Okay, we are going to do equilibrium, talk about equilibrium. That is the next big topic in chapter 7. So to kind of open this discussion, I'm going to ask this question: what if I have a reaction where delta G equals 0? We've been talking all about the importance of a negative delta G is unfavorable, favorable, spontaneous. A positive delta G is unfavorable, non-spontaneous. But what if delta G is 0? Then it's neither negative nor is it positive. What does that mean? And you can't actually have a reaction, where delta G is perfectly 0, but it can be darn near close. So what does it mean if delta G is about 0? Well, you would have an energy diagram that looks somewhat like this. If we have this reaction, A and B is our reactants, that makes C and D. On an energy diagram, that would mean the energy of the reactants, okay, so this would be your A plus B, is going to be about equal to the energy level of your product, C plus D, okay? Remember, we could draw energy diagrams where the products are more stable or less stable, and you can measure delta G, and on those energy diagrams, the reactants and products have different energies. But here, it's going to be about the same. You'll still have activation energy, so you get a little graph that looks about this. Then your change in energy on this y-axis is 0. There's no change between the energy level of the reactants and the products, okay? But what does that mean, okay? How does that relate to equilibrium? Well, let's keep talking. Here's what that means. What's happening is you start out, if you mix A and B, they're obviously going to react, produce B or C and D. Once you've made enough C and D, they can also bump into each other, have efficient collisions, and react to remake your reactants, okay, A and B. This is called a reversible reaction, okay? So in this case, A and B make C and D. That's our forward reaction. C and D remaking A and B, we call this the reverse reaction. So you got a forward reaction, and then now we have a reverse reaction, which is just the opposite thing here. And sometimes you'll see it drawn like this. When we combine them, you'll see this double arrow, and the arrows have little, the heads of the arrows just have little one tail instead of a double headed arrow. So that indicates a reversible reaction. Then you have your product C and D. Okay, so when you see the double arrow in the middle right here, right there, that means it's a reversible reaction. Oops. Okay. All right, so far, this is kind of the intro on what equilibrium is. You've got a scenario where delta G is getting close to 0, and you have a reversible reaction. All right. And this is what I said earlier. We said reactions don't exactly have delta G that equals 0, but can be very, very close. So you can see here A and B are slightly higher in energy than C and D, but it's pretty close. Or you can have a scenario down here where A and B slightly lower in energy than C and D, but again, the delta G is almost exactly 0. Now, this is kind of a side note, not a key note right here, this bullet point. So it's not the main point of the slide, but usually when you have this situation, the favorable reaction, the one that has a delta G that is slightly negative, is written as the forward reaction, okay? But I'm going to kind of move past that because it's just a side note here. I'm not going to ask you questions on that. Okay, so eventually what's going to happen is, here's the word rate. So we're going to key on this. The rate of the forward reaction and the reverse reactions will be the same, okay? So you're going to have C and D remaking A and B at the same rate that your initial reactants A and B are making C and D. Those rates will become the same. That's a key point here. And when this happens, when that occurs, this is an important word, the concentrations of the products and reactants stop changing. Stop changing. This is a very key point because it's both underlined and bold. Both, when this happens, both the forward and reverse reactions still occur. It's a very dynamic scenario here. That doesn't mean the reaction just stops, but because they are occurring at the same rate, there's no change in concentration. Now, we've mentioned this word concentration briefly yesterday when we lectured on this, but we're going to dive into it a whole lot more today, okay? This is what we call an equilibrium. when you have two reactions happening, a forward and a reverse reaction, and they're happening at the same rate. Okay? I'm going to give you an example in just a moment to maybe help explain this if your head is spinning right now. Okay, so this is the actual definition of equilibrium. The state where the forward and reverse reactions occur at the same rate, so there is no change in product or reactant concentration. All right, and again, we draw these reactions like this, the forward and the reverse with the double arrow. Okay, I'm going to hit this point again. Does not mean equal concentrations. Equilibrium does not mean that. It just means equal rates. It's kind of like this. I love this analogy with the escalators. Okay, I'm going to zoom in on these escalators in a second. Okay, some of you are still writing. If you have a mall, it looks like there's some sort of like, is that like an ice rink down in here? I'm on highlighter. Down in this mall, that would be cool. I've never been to a mall like that. This is a northern mall. This is a mall in North America. Okay. You have this mall. It's very vacant, kind of like malls are these days. I feel like malls are going to go out of style, maybe out of business in a few years. Indoor malls, that is, unless you're in North America, maybe. Okay, you have these escalators. Usually you see escalators in places like malls. Here's what I know about escalators. They move at the same rate, right? So if we had, I don't know, let's say we just have, if we had like 250 people on floor 2, and let's say we had 100 people on floor 1. Let's say somebody on floor 1, we'll call this the up escalator, and we'll call this the down escalator. All right, if we have these numbers of people on the different floors, let's say someone from floor 2 steps onto their escalator at the exact same time somebody on floor 1 steps onto their escalator. They are going to arrive at the opposite floor at the exact same time, right? Because these escalators are moving at the same rate, same speed. It does not mean that you're going to end up with, and if you just keep sending people, okay, people one by one keep stepping on the escalators at the same time, it does not mean that you are ever going to arrive at the same numbers of people on floor 1 and floor 2, okay? It just means that you're going to be sending people to the opposite floor at the same rate because the escalators are moving at the same speed. All right, that's kind of how equilibrium is. Doesn't mean you end up with the same numbers of molecules of A and B as molecules C and D. It just means that you are remaking the reactants and the products at the same rate, okay? All right, if this is still confusing to you, my last ditch effort here is that I put this little link. It's a TED Ed, so it's a TED Talk. Go watch this little video. Copy and paste this into your browser, and it's on equilibrium. Maybe just hearing it another way. I would encourage you to read the equilibrium section in your textbook. If your head is still having a hard time wrapping around what does equilibrium mean, what is equilibrium, it's a short video, but check that out if you're just still unsure. Okay. All right. We're going to move on to the next slide. Okay, here's the definition of equilibrium at the top. I'm going to look just underneath this definition. So we have this reaction where it says little a big A plus little b big B makes little m big M and little n big N. So these lowercase letters are the coefficients. All right. And the capital letters are your reactants and products. So when we have an equilibrium, you see the double arrow, we can write an equilibrium equation. All right, and that equation is shown to you right here. I'm going to zoom in on it a little bit. You have this letter K, which we call the equilibrium constant, and then it equals all this stuff, and this stuff looks really complicated, but it's not. K equals, let me break this down. On the top, so obviously we have a numerator and a denominator here. On the top in the numerator, we have the concentration of your products. So that is M and N, capital M, capital N, because those are your products. Raised to the power of, raised to the power of your coefficients, okay? These are the exponents. The coefficients become exponents. So let's say concentration of M is like 0.5 moles per liter, something like that. We'll define concentration in a minute. And then let's say we have a 2 in front of our M. What that would mean is you would have 0.5 raised to the power of 2. You'd square it. All right, so it's just an example. We're going to dive into this more and work more examples of this in a minute. I'm just kind of showing you how to plug numbers in. All right, so on the bottom, you have the reactant concentrations, A and B, raised to the power of their coefficients. Remember, the lowercase letters are the coefficients. All right, so concentration of products raised to the power of their coefficients, divided by the concentration of the reactants raised to their coefficients. And these things are multiplied, okay? So it's A raised to the power of its coefficient times the concentration of B raised to the power of its coefficient. All right, so you got to make sure your equation is balanced so that you have the right coefficients. And then same on the top, the M and the N, it's all multiplied. Okay, so we've been using this word coefficient, we've been using this word concentration. What does that mean? Concentration, we talked about the example with lemonade, if you've ever had bad lemonade. It's because the thing that is dissolved in the water to make the lemonade, the powder with the sugar, it's not strong enough. There's not enough of it. Okay, so concentration is a measure of an amount. Okay, so it's an amount of this word solute. And this is the stuff that is dissolved. The stuff that is dissolved is your solute per a volume of solution. All right? So it's amount of solute, whatever you're dissolving, in a volume of your whole solution. And the solution contains both the solute plus the solvent. Okay, which is usually like water or the liquid that you're using to dissolve your solute. Okay? So that's just the generic definition of what concentration is. But there's different ways we can measure concentration. We're really going to dive into these things in Chapter 9. I'm just giving you a brief intro since equilibrium involves this word concentration so much. So the first way you can measure concentration is with a weight volume percent. We abbreviate it WV percent. And the definition of that, it's grams. Okay, grams is an amount of solute per milliliter of solution. I'm going to abbreviate SOLN. So grams of solute per milliliter solution times 100. Okay, don't forget this times 100. That turns it into a percent. Okay, the times 100 turns it into percent. Okay, you can also measure concentration in units of molarity. We abbreviate molarity with a capital M, and that is going to be moles of solute per liter of solution. All right, so we just have different units here. We don't multiply this one by 100, but moles of solute per liter of solution. Okay, notice solute always goes on the top, either in grams or moles, and then the volume of your solution always goes on the bottom. Okay, so that is how you measure concentration. That's a little bit of what concentration is. So let's talk a little bit more about this equilibrium constant K. Here is our equation again, A and B make M and N, and then here's our equilibrium expression of that. I'll call this an equilibrium equation or expression. The expression for K, okay, all of that just means this equation over here. K is your constant, and notice it's a constant, okay, so it doesn't change if you have a particular reaction. No matter what your concentrations are for your reactants and products, K will always be the same no matter how you calculate it. What does this statement say right here? I can compare the equilibrium state. Okay, what does that mean? What is an equilibrium state? Well, I'll define that in just a second. Of two experiments using an equilibrium equation. So let's say we have this equation right here where we have SO2, it's a gas, and we have O2, oxygen, it's also a gas, and that makes SO3 gas. And it's balanced. Okay, we got a coefficient of 2 in front of SO2, a 1 in front of oxygen, and 2 in front of SO3. So when you write the expression, remember the concentration, and these brackets right here, these little brackets, Anytime you see brackets around something, that means that's where you plug in the concentration of that thing. Now, we are not given numbers. Concentration is going to be some sort of number with a unit of, where did my slide go? There it is. With a unit of weight, volume, percent, or molarity. And we don't yet have any concentrations given to us for this SO2, SO3 equation. I'm just showing you how you write the expression for K. On the next slide, we'll plug in some actual numbers. So the concentration of SO3 goes on the top, and we got a coefficient of 2, so that's why we write this little 2 right here. We square it. And on the bottom, we plug in the concentration in brackets of SO2, and we have a 2 in front of SO2, so that's why we square it. This 2, the subscript 2, does not mean we square. That is included in my formula, okay? So we're not paying attention to subscripts here. We're just paying attention to coefficients. O2 has a coefficient of 1, so we don't put anything as the exponent in our equilibrium expression for O2. All right, I'm going to erase all my scribbles so you can see this equation clearly. Okay, like we said, K is the equilibrium constant. And what does K tell us? We said it tells us about the state at equilibrium. What the heck does that mean? K tells us about the ratio of reactants versus products at equilibrium. Okay, so at equilibrium, are we going to have more people on floor 2, or are we going to have more people on floor 1? Okay, that's the escalator, going back to the escalator analogy. In other words, at equilibrium, even though we have the same rates, do we have more reactants or more products? Okay, whichever reaction is the favored reaction, consider that energy diagram again. Okay, if you have your reactants have that much energy, and let's say your products just have slightly lower energy, so your delta G is almost 0, but it's not exactly 0, well, the forward reaction will be the favorable one because you want to make things that are more stable. And here, products are lower in energy, which means they're more stable, just by a little bit, okay? Okay, but in this case, you'd have slightly more products because products are more stable. It's going to favor the reaction that's giving you the things that are more stable. So anyways, K tells us about the ratio of concentration of reactants versus concentration of products. What do you have more of at equilibrium? K also tells us whether the forward or reverse reaction is more favorable. And I feel like this is kind of redundant of point number 1, but slightly different. If you have more products at equilibrium, then the forward reaction will be favorable. I'm going to say that again. If you have more products at equilibrium, the forward reaction will be favorable. I'm going to do a little highlight action here maybe to help explain this. Let me erase all my scribbling. So I'm gonna highlight in blue. If you have more products, higher ratio, more products at equilibrium, then it's the forward reaction that's favorable. If you have more reactants, if your concentration of reactants is higher at equilibrium, then the reverse reaction is more favorable, okay? I hope that highlighting helped. Okay, so again, I said we don't have any numbers for SO3, SO2, and O2 just yet, but on this next slide we do. If I'm going too fast and you need to slow me down, just pause this video, rewind it, rewatch, but I'm going to keep moving on so this thing is not an hour long. Okay, let's say now we actually have some numbers, okay? Let's say we have these numbers right here. At equilibrium, we have 0.062 molar, that's mole per liter, SO2, 0.538 molar oxygen. That means we're talking about units of molarity here, and 0.938 molar SO3, okay? You could plug these things in. All these numbers would just go right up in here in this equation, and you would calculate K, okay? So the 0.938 would go on top where SO3 is, and you would square it. So we could write this out. 0.938, square it. That's the SO3. Products on top, reactants on bottom. Then it goes 0.062 molar, and that's for SO2, and we square SO2. I'm rewriting this reaction right up here, plugging the numbers in. And then you have the concentration of oxygen. So we're multiplying that by the SO2 concentration in the bottom. So that's 0.538 and we molar. And we don't have any coefficient on O2, so we don't have to square it or anything. And then you would calculate K. And for experiment 1, if you did that, your K should be 425. So actually plug that into your calculator if you want. Double check. You should get a K of 425. For experiment 2, you have these different numbers. Okay. Notice for experiment 1, it looks like you're mixing 1 molar SO2 and 1 molar O2. So you're starting with all reactants and you're running the reaction this way. And then eventually you reach equilibrium where you have a reversible reaction. Experiment 1, you're just starting with only product and you're running the reaction in the reverse order, but eventually you reach equilibrium. And here are the equilibrium concentrations. That's what we're plugging into the reaction. So you would rewrite the reaction for experiment 2, plug these numbers in, the 0.15 molar, 0.0751 molar, 0.850 molar, just the way we did for experiment 1. I'm not going to take the time to write all that out. But when you do that and you square everything properly, products on top, or product here on top, product or reactants on bottom, you should get a K that's 428. Now I know you're like, that's not the same number, but remember we have human error. If you're actually doing this in the lab, there's going to be a little bit of error because we're humans and we sometimes make mistakes in the lab. So these are within, what just happened? These are within experimental error, these two numbers. Okay, so it's trying to prove to you that K is a constant with a small amount of human error. All right. We're going to do some actual practice problems in just a minute. I got one more slide I want to explain a little bit more about K. So we said K tells us the ratio of concentration of reactants and products at equilibrium, and it tells us if the forward or the reverse reaction is favorable. Okay, so all of this up here is just some review stuff. Okay, it's just pictures I've had on previous slides, but I just have them here for you to reference and look at as we talk. I really want to key in on these color-coded statements. This is a figure directly from your book right down here. So you can look at this in chapter 7. I forget what section it is, the section on equilibrium. But in blue, if K, when you calculate K, so like right up here, we got K that was 425 and 428. So this would correspond to the statement that is blue because K is larger than 1. If your K is bigger than 1, what that means is at equilibrium, you have a lot more products. The concentration of products is higher, greater than the concentration of your reactants. If that's the case, forward reaction is more favorable because your products are going to be more stable, a little bit more stable than the reactants. Okay? All right, that corresponds to this section of the arrow. Okay, if your K is somewhere between 1 and what's 10 to the 3? 10 to the 3 is 1,000. So if you get a value of K that's between 1 and 1,000, then you can say this right here about equilibrium. Concentration of products is greater than concentration reactants. Forward reaction is favorable. If you have a K value that's much, much bigger than 1, between 1,000 and, I guess, infinity, very, very large. If you have a K that's like 10,000, 100,000, 5,000, really, really big, what that means is that you have pretty much all products. And like very little or no reactants because the reaction just goes all the way to completion. Okay, because K is so big, which must mean that the top number here is a lot bigger than the bottom number. Okay, so that means you have more products if the top number is bigger because that's where the numbers for the products go. That's why we get a really, really big K. So that's why we say the reaction goes to completion, you have all products. Okay, orange statement. If K is less than 1, okay, so that corresponds to this portion of the arrow where your K is between 1 and, we're not talking a negative number here, we're just talking decimals now. 1 and 0.001, that is 10 to the minus 3. When that's the case, you have more reactants than products, right? So the concentration of products is now less than the concentration of the reactants. And so the reverse reaction is favorable. Lastly, if your K is way, way, way smaller than 1, so less than 0.001 and just keeps getting smaller. So maybe like 2 to the minus 10 or 1 to the minus 12, okay? 1 to the minus 5, any of numbers like that. are way, way, way smaller than 10 to the minus 3. So here, the reaction hardly happens at all. Just the forward reaction does not occur. You have all reactants at equilibrium. So the whole point that I want you to do from this, I want you to be able to, if I give you numbers, like up here, if I give you a set of numbers like this and a reaction, I want you to be able to, one, write out the expression for K, okay, which would be something like this, depending on what your reaction is. Then two, I would want you to be able to calculate K. I will give you the numbers, and you just plug them into the expression you've written, and you calculate K. Then, thirdly, I would want you to make a statement about, in capital EQ stands for equilibrium. Make a statement about equilibrium. Tell me, do you have more products or more reactants? Tell me, is the forward or the reverse reaction favorable? This is what I want you to be able to do with equilibrium from the stuff we just talked about. Okay, again, if I'm going too fast, pause the video, rewind it, rewatch. I'm going to move on. Let's put this into practice. So here's the question. What conditions would you expect to find at equilibrium for these reactions? Number one, we have hydrogen and oxygen gas making water, and my K, it's already calculated for you, 3.1 times 10 to the power 81. Holy moly, that's huge. Okay, this corresponds to the statement in purple, right? It's way bigger than 10 to the power of 3. I'm going to highlight this in purple, okay? So this would correspond to the, of course, this would correspond to that statement in purple. So what that means is reaction goes to completion. Or you could say forward reaction favorable. Or you could say more products than reactants, or all products. All right, next one, number two. We have nitrogen and oxygen make nitrogen monoxide. And your K is 4.7 times 10 to the power of negative 31. That is really, really, really small, so that corresponds to the statement in red. So we're going to highlight that red. And what that means is the reverse reaction is favored. And you essentially have all reactants. Okay, the forward reaction does not happen. Number three, you have CH3CO2H, acetic acid, plus CH3CH2OH, and you make these products. And your K is 3.4. It's really, really close to 1, but it's slightly bigger than 1. It's between 1 and 1,000. So that corresponds to the blue statement, right? So we're just going to, how many times do I do this? Just going to highlight that blue. So then you would say forward reaction favored. And you could say concentration, I'm going to abbreviate, P for products, is greater than concentration of reactants. Okay? So I would want you to be able to look at a K and then make statements like this based on the size of it. Or if I give you concentrations of everything, plug them in to an expression, calculate K, which is what we're going to do next. Imagine that. Water and methane, carbon tetrahydride, react to form carbon monoxide and hydrogen gas. Write the balanced chemical reaction. Then write the equilibrium equation for the reaction. Then if K is 2.5 times 10 to the power 6, are the reactants or the products favored at equilibrium? Okay, let's just do this one step at a time. Write the balanced chemical reaction. So we got water. We know what water is, H2O. Methane, which is carbon, tetra is the prefix for 4, hydride is 4 hydrogens. So that's plus CH4. And this is a reversible reaction because we have an equilibrium here. That's going to make carbon monoxide, CO, and hydrogen gas, which is a diatomic. We need to make sure this is balanced because it's not right now. So I think we've got 6 hydrogens on the reactant side. We need 6 on the product side, so I'm just going to put a 3 there. Then we're good. Okay. So we're going to write the balanced chemical reaction. Let me get a drink. By the way, I realized I forgot one thing. It's important to know the states of matter. Water is going to be a liquid. CH4 is methane, is a, put a gas right there. Carbon monoxide is a gas. Hydrogen is gas. In your equilibrium expression, this is a very, very important note. I'm going to put a star by it. You only include things that are gases or aqueous in the equilibrium equation or expression. We do not actually write things that are liquid, okay, or solid. So don't include liquids or solids. Okay, there's a little blurb about this in your textbook if you want to know more about why. But we only include things that are gases or aqueous. So what I encourage you to do is write out your balanced reaction, then go through and highlight the things that you need to include in your equilibrium expression. And I'm only going to highlight these 3 things because we're only going to include the gases or things that are aqueous in our equilibrium expression. So I got part 1 done, got the balanced equation. Now I'm going to do part 2. So this was part 1. Part 2, write the equilibrium equation for the reaction. So that is the K. K equals, people get confused when I say, excuse me. People get confused when I say write the equilibrium equation. I'm not talking about the balanced chemical reaction. We've already written that part. Now we're talking about the equation for K. So we're going to plug in the concentration. I don't have any numbers that I'm plugging in. I'm just writing the concentration of CO. And we don't have any coefficients for carbon monoxide. So just write CO. I don't have any to raise it to the power of anything. Times the concentration of H2, and I got a coefficient of 3, so I'm going to do it to the power of 3. Then in the bottom, I'm not putting water because it's a liquid. I'm just putting the concentration of CH4. And I don't have any coefficients, so I don't raise it to the power of anything. And that's it. That's part 2. So this was part 1. This is part 2. Now part 3. If K is 2.5 times 10 to the power of 6, which is much, much greater than 1, right? Are the reactants of the products favored? Go look at that color-coded arrow. That corresponds to the purple section. So you're going to say what purple says. Reaction goes to completion, which means products are favored. I'm going to erase all my scribble and just highlight it. Products are favored. Okay. All right, and that's it for equilibrium. So I probably went over 15 minutes. I'm sorry if I did. That's equilibrium. I'll give you some practice problems on this, but the next video we're going to talk about